Hey everyone, in this video we're going to talk about section 4.6, which is about graphs of rational functions. So we're going to extend what you learned about rational functions in Algebra 2, and we'll also revisit limit notation and use it to discuss behavior of rational functions at different key locations. So let's talk limit notation first. So far in this class, we've only ever used limit notation to discuss our end behavior. What happens at positive infinity to our function, what happens at negative infinity to our function. Well, we can also use limit notation to discuss what the behavior of a function is like at a certain point. So what happens when x is approaching a non-infinite value? Drawing myself a little picture, we're going to be taking a look at this, and I'm going to describe it with a. So a represents like an x value, and wherever we see an L represents a y value. Okay, so if we see the limit as x approaches a, and then we have a this plus here, that means we're talking about the limit as x approaches a from the right. So we're discussing the function behavior, what happens as we get closer and closer and closer to that function at a, or from a from the right, and it's approaching this value, this y value L. Now here's the deal, we don't actually even need a point there, we're just discussing what's happening to the function to the very right of it. If we see a negative here, limit as x approaches a, and we have that negative, that's talking about it as approaching from the left. So what is the function doing as we get closer and closer and closer to the left? Okay, again, it's not what's happening at that point, it's what's happening to the very left of it. Now, if we don't see a plus or a minus and we just see an a here, that's talking about the limit as x approaches a from the left and the right. Okay, so if we're going to have this last one, if we're talking about just the limit as x approaches a, it has to be matching and coming to the same y value from the left and the right. It has to be approaching that same value. We're going to look at that in just a moment, but since we're talking rational functions, I do just want to give you a couple of reminders about horizontal asymptote rules. So as a reminder, degree in the numerator, if it's greater than the degree in the denominator, we've always said before that this means that there's no horizontal asymptote. In class, after you watch this video, when we discuss in class, we're actually going to talk about how it doesn't necessarily mean that there's just wild behavior. It does follow some sort of rule and some sort of pattern. We're going to say that we have a slant or an oblique asymptote. So we'll discuss in class how to find that slant or oblique asymptote if there's no horizontal asymptote. When your degree in the numerator and then degree in the denominator match, we say that that our horizontal asymptote is the ratio of leading coefficients. So for instance, in this example, our horizontal asymptote would be 3/4. Okay, and today we'll talk about why that works. And then last one, degree of the numerator is less than the degree of the denominator. We've always said before that our horizontal asymptote is y equals 0. However, this is only true unless our function has been vertically shifted up or down. Okay, we'll look at that in just a second, but let's go ahead and let's go back to limit notation first. All right, in this first example, we're going to analyze the graph of this rational function, and we're going to complete the limit statements. So looking at this rational function, it looks to me like we have a vertical asymptote at 4. So that's just something to keep in mind. Okay, so our first limit statement is the limit as x approaches positive infinity. Well, that's talking about end behavior, okay? So what happens as our x values are getting greater and greater without bound? Well, it looks to me like our function's y values are approaching 0. Might not ever reach 0, but they look like they're going to approach 0. The limit as x approaches negative infinity, okay, again, that's going to be talking about our end behavior. What happens as our function values continue on this way, to the left, without bound? Well, in this case, it also looks like it's going to be 0. Maybe won't ever reach 0, but it's getting closer and it's trending towards 0. The three new ones are going to use our new end behavior, or our new limit statements that we were looking at. So we have the limit as x approaches 4 from the left. So if I'm tracing my function, okay, and I'm getting closer to 4, but I'm going from the left side of it, where are my y values going? Well, it looks like they're going to continue down. They're never going to stop. So I'm going to say that that limit is equal to negative infinity. If I'm looking at the limit as x approaches 4 from the right, okay, so tracing it as I'm getting closer and closer this way, well, where are my y values going? They're going to positive infinity. Okay, so if I'm looking at the limit from the left and I'm looking at the limit from the right, I see that they don't match, right? They're not going in the same direction. So I'm going to say the limit as x approaches 4 of our function f of x does not exist. Okay, because the two limits from either side aren't going to the same location. Okay, from here, we're also going to write our limit statements, but we don't always necessarily need a graph to do so. We're going to define the domain of each function, and then we're going to use limits to illustrate the horizontal and vertical asymptotes. So similar to what we were doing in the last one, except this time we don't have a graph, and that's okay. We actually don't need a graph to be able to do so. So our first function is f of x equals 1 over x minus 2. I know that domain restrictions are going to come from what's going to make the denominator equal to 0, and the only value of x that's going to do that is going to be 2. So x cannot be equal to 2. That means that we have a vertical asymptote at x equals 2. So the domain of our function is going to be negative infinity to 2, union 2 to infinity. Okay, going ahead, let's go ahead and start writing our limit statements for this. So we're going to have the limit as x approaches 2 from the left of f of x. The limit as x approaches 2 from the right of f of x, and then the limit as x approaches 2 of f of x. All right, so there's a couple different ways that we can go about this. If you have access to a graphing calculator, you could go ahead and graph it, but I don't necessarily think we need to do so. So here's what we're going to do. So I always like to think about it number line wise. So here's 2, okay? If I'm trying to figure out the limit as x approaches 2 from the left, I'm just going to pick a value that's close by it to the left. So maybe like 1.9. Okay, and if I plug that into my function, I'm going to have 1 over 1.9 minus 2. Well, that's going to be equal to 1 over, let's see, negative 0.1. And so if I divide 1 by negative 0.1, that's going to give me a pretty big negative number. Okay, if I pick a number that's even closer to 2, but on the left, maybe that would be 1.99. So if I plug that in, I'm going to have 1 over 1.99 minus 2. Well, that should be 1 over negative 0.01, okay? And that's going to give me an even bigger negative number. So I see that if I continue to get closer to 2 from the left of it, I see that my numbers are going to get super large, but they're going to also be negative. So I guess in that case, you can argue that they're going to be super small. So basically, we're going to say that the limit as x approaches 2 from the left is going to be negative infinity. Okay, if I go ahead and I flip this around, we're now going to take a look at 2, but we're going to go from the right of it. Okay, so maybe I choose 2.1. Well, if I do 1 over 2.1 minus 2, that'll be 1 over 0.1. Okay, if I divide 1 by that, that's going to give me a really big number, but it's going to be positive. And if I choose something that's even closer, so like, let's say, for instance, I choose, oh, everything went away. Let's say I choose 2.01, and then I would have that would give me 1 over, let's see, 0.01. Well, again, that's going to give me an even bigger positive number. So that limit is going to go to positive infinity. And again, if I'm looking at these two, negative infinity, positive infinity, my limits from the left and the right don't match. So I'm going to say that the limit as x approaches 2 does not exist. They're not approaching the same value around it. Okay, and that should make sense knowing that what the behavior of vertical asymptotes usually does. Now, that was our limit behavior for the vertical asymptote. We can also find our horizontal asymptote. Okay, so looking at our horizontal asymptote, I see that the degree of the numerator is bigger than the degree of the denominator. Wow, backwards. The degree of the denominator is bigger than the degree of the numerator. So that means that our horizontal asymptote, I'm not seeing any sort of shifts around here, is going to be y equals 0. So for our limit statements, I'm going to say the limit as x approaches negative infinity is equal to 0, and then the limit as x approaches positive infinity is equal to 0. Okay, and I know that I said that kind of as a blanket statement. However, we could choose super large or super small numbers to plug in for f, and we can kind of see what happens there with our end behavior. Okay, that's example A. Example B is fairly similar. I encourage you to go ahead and try example B on your own and write your limit statements there, and we can check over that in class together. Let's go ahead and flip over our page. Okay, so for this example, we're going to describe the transformations that exist on this function according to the parent function g of x equals 1 over x. Then we're going to identify the asymptotes, and we'll use end behavior to describe those asymptotes, okay? So here we go. So our function is 2 over x plus 5. So when we're talking about transformations, I'm talking about, are we horizontally shifting? Are we vertically shifting? Are we vertically stretching? Like, what are we doing to this, okay? So we're comparing it to 1 over x. So there's a few things that I could do. Well, I know that this would be equal to 2 times 1 over x plus 5, okay? So when we're looking at this 2 right here, well, I know that 2 is multiplying my function, so that 2 is going to represent our vertical stretch by a factor of 2. Okay? And then if we're looking at our x plus 5, well, that plus 5 is going to tell us that we are shifting to the left 5. Okay? Going ahead and finding our asymptotes, so horizontal asymptote, I see that our degree in our denominator is bigger than the degree of our numerator, so our horizontal asymptote should be y equals 0. And our vertical asymptote, if we have 2 over x plus 5, well, I know that x cannot equal negative 5, so our vertical asymptote will be negative 5. So if we have all of this, we should be able to write limit notation describing the behavior of both of these asymptotes. So we should have our horizontal asymptote, the limit as x approaches negative infinity of f of x, the limit as x approaches positive infinity of f of x. So those are our horizontal asymptote ones. And then we should be able to also do the same thing for our vertical asymptotes. So go ahead, pause the video. I want you to find all of those limit statements and then unpause when you are ready to check, and we'll go over it. All right, welcome back. Let's go ahead and check. So our two end behaviors, since our horizontal asymptote are 0, the limit as x approaches negative infinity and x approaches positive infinity should both be 0. And then our our behavior around the vertical asymptote, approaching negative 5 from the left should be negative infinity. Approaching negative 5 from the right should be positive infinity. And then, of course, since those two don't match, the limit as x approaches negative 5 should not exist. So now that we have all of this information, we are going to go ahead and we're going to sketch a graph here, okay? So to sketch our graph, there's a few things that we know. We already can go ahead and put our vertical asymptote at negative 5. Okay. I always recommend that when we graph a function, we're going to choose points that are going around that vertical asymptote. Okay, so instead of choosing points around 0, like negative 2, negative 1, 0, well, that's going to ignore all of the points on the other side of the vertical asymptote. So I would say let's maybe choose negative 7, negative 6, negative 5, negative 4, and negative 3. Okay, just a couple of points around that vertical asymptote, including it. If we need to add more, great. If not, we're okay. So here will be x, and here will be y. So looking at our function, well, I know negative 5 will be undefined because that's the vertical asymptote. Plugging in negative 7, we should get negative 1. Plugging in negative 6, we should get negative 2. Plugging in negative 4, we should get positive 2. And plugging in negative 3, we should get positive 1. So if I go ahead and graph my points right here, negative 7 will be at negative 1. Negative 6 will be at negative 2. Okay. Negative 4 will be at positive 2. And then negative 3 will be at positive 1. So I have a couple of points here. Now, before I go ahead and I start connecting them, let's also add in our horizontal asymptote, and we also need to see if our function is going to cross our horizontal asymptote, because it can do that. So our horizontal asymptote is y equals 0. Now, okay, how do we determine if our horizontal asymptote is crossed? What do we do? Well, we know that we're trying to figure out if there's any points where we have a y value of 0. Is there anywhere where that horizontal asymptote is being crossed? So we're going to go ahead and we'll set our function equal to 0, and we're going to see if we can solve for x. Okay, so 0 is equal to 2 over x plus 5. Well, solving this, I know I need to multiply x plus 5 to both sides. Okay, well, anything times 0 is 0, so that leaves me with 0 equals 2. 0 is not equal to, so that means that our horizontal asymptote is not crossed. So in that case, since it's not crossed, we're good to go ahead and just connect everything together. All right, we're doing great. When you are ready, go ahead and flip over to our next page. All right, okay, so here's the deal. We're going to look at another example. However, we're going to have to do a little bit more to this one. So if it appears that a rational function can't be graphed simply by using transformations, we're going to go ahead to use synthetic division and long division to rewrite the rational function. So what do I mean by that? Well, our other function that we were looking at, I could see that we had the vertical stretch by 2, and I shifted left 5. So it was like I took my normal graph of 1 over x, and I applied these transformations to it. We shifted left 5, and then we stretched it by 2, so it got taller and skinnier. Well, with this one, I can't necessarily tell what my transformations are right away, because I can't just pull out my 2. I have an x on the numerator as well. So this is where we're going to use division to help us rewrite this into a different form where we can identify our transformations. So here's what we're going to do. We're going to use long division, and it really doesn't matter, but long division I think will be the better one. Okay, so we're going to divide x minus 3 into 2x plus 1. So here we go. What do I need to multiply x by to get me 2x? Well, I need to multiply by 2. So I'll have 2x, and I'll have minus 6. If I change my signs, my x's will go away, and I'll be left with 7. Okay, well, so we got to 7, and we only got 2, so what does that mean? Well, I'm going to write this as 2 plus my remainder was 7, so that'll be 7 over x minus 3. Divided by my divisor. Or I know that I can also rewrite this as 2 plus, if I pull out my 7, that'll be 7 over x minus 3. Or rewriting this one more time into a form that we're familiar with, that'll be 7 times the quantity 1 over x minus 3 plus 2. So now that we've divided, we did that pretty fast, but now that we've divided, we've rewritten this into an equivalent form. So this function here and this function here are the same function. They just look a little bit different. Okay, so now my new function, or my new form, I guess I should say, allows me to better identify what my transformations are. So for instance, sorry, there's a car honking. That 7 that we have right there tells me that we have a vertical stretch by 7. Okay, my x minus 3, that 3 tells me that we're shifting right 4. Wow, shifting right 3. Okay, and then my plus 2 tells me that I'm moving up 2. So I'm better able to identify what my transformations are. Pretty cool, because we wouldn't have gotten that from the original function. So now that we have this, let's talk our asymptotes, and we'll talk our limit notation, and then we'll go ahead and graph it. Okay, horizontal asymptote. Well, we know before that our horizontal asymptote comes from, since our degree in our numerator and the denominator are equal to each other, that's going to look at the ratio of the leading coefficients. So that'll be 1 or 2 over 1. So our horizontal asymptote is 2 over 1, which is just equal to 2. Now, I had mentioned before that we could find our horizontal asymptote by taking a look at how we've shifted our graph. Well, our original parent function has a horizontal asymptote at 0. So when I've identified that we're shifting our function up 2, that means that the horizontal asymptote will also shift with it. So that's why the ratio of the leading coefficients ends up the way that it does. Okay, so our horizontal asymptote is y equals 2. Vertical asymptote comes from where our denominator can't be equal to 0. That's going to come from positive 3. So our vertical asymptote is x equals 3. Okay, I want you to go ahead and pause the video. I want you to write out limit notation that describes the behavior around both of our asymptotes. So go ahead, pause it. Okay, going ahead and checking our answers, our end behavior limits going to negative and positive infinity should both be 2. That matches our horizontal asymptote. The limit as we approach our vertical asymptote from the left is negative infinity. Limit as we approach our vertical asymptote from the right is positive infinity. And again, since those don't match, our limit as x approaches 3 does not exist. So now that we have all of that, let's go ahead and we'll start graphing this. So we know our horizontal asymptote is at 2. We know our vertical asymptote is at 3. Okay. Let's go ahead and let's see if our horizontal asymptote is crossed. So again, that's going to mean I'm going to take my horizontal asymptote and I'll set it equal to my function, and we'll see if there's any values of x where this occurs. Okay. So if I go ahead and I multiply that denominator over, that's going to give me 2x minus 6 equals 2x plus 1. If I subtracted out my x's, I see that both of my x's would go away, and there's no way that negative 6 is going to equal 1. So our horizontal asymptote is not crossed. Good news for us. Okay. I guess not good news. I don't know if it'd be bad news for us if it was crossed. I guess it's just a fun fact that we've learned. Okay, making our table of values, since our horizontal or our vertical asymptote's at 3, let's choose a couple of points around that we can use. So let's maybe choose 0, 1, 2, 3, 4, 5, 6. It doesn't really matter how many points you choose. You just want to be able to get a good shape of what your graph is going to look like. Okay, so I know that 3 is undefined. Okay, go ahead and, again, let's pause the video. I want you to go ahead and fill out your table and then graph it, and then I'll unpause and we can check our answers together. So you're doing great. Go ahead. All right, here are the points from my table, and I've gone ahead and graphed those. So I see that the points that we have don't really get us very close to our horizontal asymptote. That's okay, as long as we know which way it's trending, we can kind of fill those blanks in for ourselves. So for instance, I can see that these are trending this way, and I'll add my arrows to show that it's just going to keep going. And then I know I'm going down this way, and I will go up here without crossing my horizontal asymptote. So here's my graph of this rational function. When you're ready, we're going to turn over our page one more time. We're going to look at a couple of more examples. Okay, for example 5, we're going to find the asymptotes of this function and then use limit notation to describe the function's end behavior. All right, I've changed this just a little bit, so if it's not changed in your notebook, you should go ahead and update this yourself. Let's do the function f of x equals 2x squared minus x over x squared plus x. Okay, so finding let's do our horizontal asymptote first. Well, our horizontal asymptote is going to come from looking at the coefficients, since both of my terms are x values, or are x squareds. So our horizontal asymptote will be that ratio, so it'll be 2 over 1. So our horizontal asymptote is y equals 2. Looking for our vertical asymptote, well, let's see if we can factor this. Well, I know that from the numerator I can factor out an x, so that's going to leave me with 2x minus 1. And then in my denominator, I can also factor out an x, so it's going to leave me with x plus 1. So in this case, I see that I have the same factor of x in the numerator and the denominator. What does that mean? That means, hopefully you answered. I don't know. I'm not with you, so I can't say. That's going to be a whole. Okay, so we have a whole at x equals 0. So if this question's just asking for a vertical asymptote, I don't necessarily want to say x equals 0 because technically that's not a vertical asymptote. That's a hole. That's something different, okay? So my only vertical asymptote is going to come at x equals -1. But I'll just go ahead and say we have a removable discontinuity. Okay. So I know that we could write our limit notation for the horizontal asymptotes and the vertical asymptotes. We've already done that in a bunch of other examples. So what I want to talk about is I want to talk about the limit notation around that hole. So we have a hole in our function. So in this case, we also can write end behavior of what's going on with that hole. I guess not end behavior, but behavior of the function around that. So I'm going to write the limit as x approaches 0 from the left of f of x. The limit as x approaches 0 from the right of f of x. And the limit as x approaches 0 of f of x. Okay, so we can also describe what's going on around that hole. So, again, I like to think number line. Okay, here's 0. We're going to choose the values that are close on one side. So let's say negative 0.1 and then positive 0.1. If I evaluate the functions at these values to the left and to the right, I'm going to get negative 1.33 repeating, and then I'll get negative 0.727 quantity repeating, okay? And so from first glance, it looks like, okay, the limit from the left and the limit from the right are not going to approach the same thing. Well, not so fast here. Remember that this is going to be a rational function, and so since we only chose these values, we can get closer and closer from the left and from the right. So if we identify and look at the graph of this function, I do see here that our function, as we approach 0, is approaching the same value from the left and the right. Now, if I go and I trace, let's see if I can see it. Oh, come back. It tells me that at 0 we are undefined, but I see that from the left and the right we are approaching the same thing. And it does look like we're approaching -1. So in this case, I will say that the limit as x approaches 0 from the left is -1. The limit as x approaches 0 from the right is -1. And then the limit as x approaches 0 is also going to be -1, or is also going to be -1 because these match. Okay. A way to do this without looking at our function is to take a look at what we were left over with after we took out that hole. So that left us with 2x minus 1 over x plus 1. If I evaluated this at 0, that'll give me -1 over 1, which is in fact -1. So our function is going to act like the same function, just without that hole. So that's a way that you can find that as well, algebraically. All right, we have made it to our last example here. So example 6 is we're going to graph this function by finding the intercepts and asymptotes. We're going to use limit notation to describe the function's end behavior at each asymptote. I'm going to go ahead and I'm going to pause our video here. I would like you to try question number 6 on your own and then be ready to go over it at the beginning of next class so we can check our answers. So that's all for this video. I will see you all later.